this notebook has been set up in a way that anybody can come in, read all the information they need, and then be able to run the data on their own. So there's some information on where to find the documentation, where to find the GitHub repo and set up your repository, set up your JWST install. Goes through the basic steps we'll be following, the steps you might need to do before getting started, and then information on how to run the pipeline. One thing you will need to note is you will need to set your CRDS environment. So you need to tell the computer, or the notebook, where to find your CRDS path. This is where you store your CRDS reference files, and then where to look on the server. So you would set this up if you don't have it preset in a setup file. We will be working with data models. So this is the basic block that we use to store data. You will find the header data in the .meta extension, science data in the .data extension, and data quality flags in the RAMP model can be found in the group DQ, which allows you to find the DQ flag of each group in the data, or in the image model, you'll find it in the .dq extension. And there's information on where to find more details on the data models. The only things this notebook needs installed is JWST and Jupyter. Now, if you're going to run these, I've done all the running ahead of time, but if you would like to run your data, run the notebooks along with me, you will need to start with the first cell to download the data. And step 2 is import, this to set up your CRDS environment. Then you'll just need to import the JWST modules. So we'll be importing detector 1, image 2, and image 3. And for the data models, this notebook uses RAMP model, image model, and the DQ flags. This block is needed in order to set up association files. And the rest are usual AstroPy and Matplotlib type things. One thing I like to do in all of my notebooks is to print the JWST version so that I know what version of the pipeline has been run each time. This is a helper script to overlay catalog, which will just display the image and overlay the catalog at the end. This notebook was set up so that it can grab the data from Box. So if you would like to download this notebook and run it on a local directory on your computer, you can download the data straight from Box. This sets up the files, and the second one you would have to uncomment to actually download the data. Since we're not doing that, we'll just do an uncal listing so that we have a list of all the files that we can process. To look at the header parameters in your data, you will read each file into a RAMP model and then access the meta extension of that model. Then you can read in things like the file name, instrument name, subarray filter, and how large the data is. In this case, we have F770 data, 5 data files of 1 integration and 6 frames each. And they're full frame. If you don't know the meta extension, you can look it up by looking for the fits header keyword using find fits keyword and just say, I want to know how to find the date ups. And that will tell you how to find it using the data models. Sorry. And then just for this notebook, I pull out a sample file and get the base file name so that I can use it for uncal, jump, cal, whatever. And then we will load that RAMP model and take a look at the last extension, or last frame in the file, frame in the extension. So we look at the 0th integration, last frame, and then all X and Y values. And this is what a MIRI imager image looks like. You can see there's a lot of point sources in this one. We have the imager region on the right, the LEO in the upper left corner. Then we have 3 4-quadrant phase masks, and then some support structure holding everything in place. When we combine the image at the end, we'll only have the LEO and the imager portion left. To look at a pixel up the ramp, you just choose your pixel number and read in the .data extension, choose your integration, all frames up the ramp, and then your pixel position. So this will show you whether you have a normal ramp or if you have something strange going on or a jump has been flagged. So we come to now how to run CalWeb Detector 1. I have certain preferences in the way I do this. Everybody will have their own, so each person's notebook will look a little different. I choose to set parameters in most cases in a single block and then run the data in the next. So the parameters we're setting here are the rejection threshold, and then there's something in the jump step called shower or snowball detection. The snowballs are for near-infrared instruments, and they have expand large events. If you want to run your snowball code, you would set that to true. This is MIRI. We do it a little differently. So we set find showers to true and the near-infrared option to false. So when you come into the pipeline, you set up for each file a Detector 1 pipeline, load the file in, and then set up a configuration dictionary for any parameters you choose to set. My preference in doing this is to do everything one parameter per line so that I can comment or uncomment as needed. And you set up for each step a blank dictionary and then read in your parameters one by one. So in this case, we're setting jump save results equals true. We're setting our rejection threshold and then using the parameters previously set to set expand large events and find showers. One thing I will point out is this save results of the jump step equals true. This optional output file is extremely useful if you're doing anything like debugging something that has gone wrong in your code. If you want to look at any particular pixels up the ramp, this has a lot of useful information, but the files can be very large. So if you're simply running all of your data and you don't need to look at the optional output, don't save this file because you can fill up your disk very quickly. I have experience with doing this exact same thing. So once you have your configuration dictionary set, we will do a pipeline.call, give it your file, your configuration dictionary, say save results equals true, and then your output file name. I'm just sticking with the usual pipeline output, but if you wanted to, say, run multiple tests, you would put something like base plus jump test dot fits, something along those lines. And that's where you can do different output names. Now, the pipeline is very verbose in its output, which can be tedious if you're just running data, but if you want to look for something, it's very useful. So this will tell you every parameter that has been set. It tells you if something has gone wrong. There are some warnings that are harmless, but if there's any errors, you might want to look into anything like that. So we're going to scroll through the output. And here we go. Then we'll look at the output rate image. So again, the input to Detector 1 is a rate up the ramp image in counts, and it comes out as a rate file in counts per second. So we will read in the sample file.rate image. And one thing that has been very useful for me is to be able to look at individual pixels that have been flagged. I'd like to look at an image and say, where does it tell me there are bad pixels? So in this case, we're going to be using the masked where function. You give it your rate image.dq extension. Say, I want to find flags with the pixel value of do not use, and then give it your rate.data image. And then it will, I choose the grays color maps most frequently, and I want to set the bad color to blue. So this will show me then the rate image in counts per second with everything that has been flagged along the way as do not use. And in this case, you'll see that MIRI has a shorted column. We have some bad pixel regions. Up in the corner, we have something called the scar. And we have some other bad regions. Some of these have been flagged as do not use just through the running of the pipeline. If we want to look at a few specific ramps, say we want to know what's behind this dot. So you choose your pixel values, read in the jump file and this is the one that I said was large but very useful for diagnostic purposes. And then we'll come in and say, look at the group DQ of this jump image, which we've read into a ramp model, and look at the integration we choose, in this case 0, all pixels up the ramp, and then the particular pixel number, and tell me where it's flagged as a jump detection. So then you come in and you plot your ramp, and your ramp where it's been flagged as a jump, put a black dot. So we look at all of the pixels, and you see in the last pixel, we have a jump. And you can see visually where the jump is and where it was flagged. And if you look at the actual pixel values from the DQ array, you see that we skipped the first frame because 1 is do not use, and we have a flag of 4 in this last frame here, or second to last frame, and that's this jump detection. So this is just a handy syntax for debugging purposes. And then we'll come in and run CalWeb image 2. Now this one I tend not to change parameters. It's pretty self-sufficient on its own. There's not a lot that needs to be changed. So I just run it, call for each file, the image 2 pipeline, give it the image and save results. Let me scroll down out of that one, which we can then pull the cal.fits image, which is the calibrated image in Megajansky's per steradian. And I'm just going to look at the rate file and the cal file next to each other. There's the rate file in counts per second, and the cal file in Megajansky's per steradian. In order to be able to run CalWeb image 3, we need an association file, which is just a file that says, I have these 5 frames, they're at different dither positions, whatever, but I'm just trying to combine these 5 frames into a final combined image. So we give it a combined name, do a glob or whatever, a listing of your file names. So I just grabbed everything with the right PID and a cal.fits. Read the list into ASN from list with the proper rule in place, and then dump it into a .json file. Then you can run CalWeb image 3. This is the one that does all of the alignment, the resampling, any sky values that need to be done. So this is probably best to be done iteratively until you've decided what your best set of parameters are. So in my case, I am going to align to Gaia DR3. TweakReg has the capability to align to external catalogs. Currently supported options are Gaia DR1, DR2, DR3, a path to an existing reference catalog, none, or just a blank field. In our case, we're going to align to Gaia DR3. This abs min obj parameter says how many stars you have to match between your data and Gaia to be considered a match. The higher the number you have here, the better your alignment is going to be, but it all depends on what your data set is. Given the number of point sources in my data, I could probably do this a much higher number. And then I want to save the output Gaia catalog so that I can look at the output later. The min obj number without the abs in front of it says how many stars you have to match between your different dither positions to consider it a final match. So in this case, I have a good number of point sources, so I'm going to leave that as 25. In this case, we have a few sample parameters that show you how to change the values, but these values that I'm using have been shown to be good options in specific science cases in which I've been involved. So the Gaussian kernel is one that I use for resampling. It's good for point sources. The scale value I'm going to double from the default because that has been useful in the absolute flux calibration program. And for MIRI, we basically need to be using weight type exp time. So then I'm going to come down here and show you how to set each of those. Given that we're combining all data into one file, we don't need to do any kind of looping. We'll just say, set these parameters and run on the association file. So we set up our configuration dictionary. And then for each step, we set up a blank dictionary, set our tweak-reg parameters for the ABS catalog to match to Gaia, and a few other parameters, the min-obj that I mentioned, and say save the catalogs out of here. If you want to skip any step of the pipeline, that is also something you can do. I'm not skipping it, so I've got it commented at the moment. But you can also say for a particular step, using the single open and close curly brace, skip true, :true, and that will skip the step. I've got the two different versions of the syntax here. So again, I like one parameter per line. So I'm doing multiple parameters with the first open the empty dictionary and then fill it in. But you can also, if you have only one parameter you want to set, use the outlier detection, open the curly brace, use the scale : scale, and that will allow you to do single parameters. If it's your preference, you can also do a long line of these. Just put a comma in between each parameter that you're trying to set using the : syntax. But again, this is my preference. I think other notebooks you'll see different things. So I set my tweak-reg parameters, my resample parameters, and my outlier detection, and then call the notebook or call the image3 pipeline with your association file, your configuration dictionary, and then say save results. We scroll through, and at the end, we have our final I2D combined data file. So we look at that, and we have a nice smooth background. We've got clear point sources, a couple little galaxies in the background, and then a bit of dust or a nebula off to the side. We can look at the catalog table, the catalog that is output as the source catalog. We'll read the table in and grab the X centroid and Y centroid values from the table so that we can plot where the catalog has found sources. And then we will read in our mosaic data, plot the X and Y positions, and you can see where the catalog has decided it found point sources. I will give a caveat that with MIRI data, and I'm assuming other instruments as well, we tend to get a little noisy around the edges of images. So I won't actually trust that this entire area is correct. I would go in, visually compare each pixel position that it says there's a star or point source or whatever, and then delete them if need be. As you can see, there are point sources here, but not nearly as many as it has flagged. If you would like to then compare to Gaia, you can see how many Gaia sources there were on your image. So you read in the Gaia DR3 catalog and print it out. You see that it found, or at least it has 2,485 target sources in RA and DEC coordinates. Now we need to get those in XY positions to put them on our image. So we do a WCS transformation, WCS.getTransform from the world coordinates to detector coordinates. And then we get our X and Y positions for Gaia by feeding in to this transform the RA and DEC values. And then we can plot X and Y Gaia positions on top of our image. The way this typically works is Gaia, they will do a cone search of the Gaia catalog that will give you point sources that fit your entire mosaic. So you see our mosaic is entirely contained within this circle, but obviously that not all of the Gaia sources in this field of view line up on our image. So if you would like to see how well Gaia and your catalog match, I like to do a little zoom in. So I choose a 100 by 100 pixel region, get my coordinates in that region, and then overplot them. So in this, the Gaia sources are marked in red with a size of 15, and the MIRI catalog is in yellow with a size of 5. So if you see on these sources a red dot overlaid by a yellow dot, we have a good alignment.